So in this video, I want to talk about Occam's razor and Bender and Koller's octopus. So to remind people about the setting. So we have two people, A and B, who communicate maybe via telegraph or whatever. Imagine they're astronomers and imagine that they basically write to each other about what they observed when. And then the octopus is reading the correspondence and it's just trying to predict the next words in the letters. So maybe A says, yesterday I looked just east of the Big Dipper and I saw whatever. And the octopus is trying to figure out what they had said. So what can the octopus do? Well, if the octopus has GPT-4, it could try that. GPT-4 would not work for that. It would predict based on the training set. It wouldn't really predict kind of astronomy. The question is, like, could you do better than that? So could GPT-5 or 6 actually do that? Bender and Koller's argument is no. Here, I'd suggest a way to argue that actually, yes, you can. But first, I want to talk about what did people do in this situation. So people have been observing stars and planets for thousands of years. And how did they think about it? Did they try to predict what's going to happen tomorrow if they go out and look at the sky? Well, so the first big idea was the geocentric model. So it seems like heavenly bodies go around the Earth. And the idea was, well, like, we just need to figure out the circles in which everything goes around the Earth. Now, that's not true. It does predict okay, just not great. And that was people's first idea. So more than 2,000 years ago, people figured out a way to do better at predicting the training set and like actually predicting the test set as well. And the big idea was epicycles. So the idea was everything still goes in circles around the Earth, but also while it's going in circles around the Earth, it's also doing those epicycles along the orbit. So if you add epicycles and then epicycles on top of epicycles, actually that works extremely well for predicting what you see in the sky. That was state of the art for prediction until Kepler. And in fact, the model that Kepler first proposed was not as good at predicting the future as the epicycles and epicycles. Of course, Kepler's theory was a lot simpler than the epicycles, so the epicycles would be like 500, 600 parameters. The reason the epicycles work is, well, one, the Earth rotates around its axis, so that kind of gives this effect as well. But for another thing, basically you have like epicycles on top of epicycles on top of epicycles. You can describe any orbit because this is kind of like a Fourier decomposition, if you know about that. So that was the state of the art until Kepler. And Kepler figured out that actually like the orbits are actually elliptical, and you saw probably in physics 180 how Kepler's laws work. So building on that, Newton came up with Newton's laws and the law of gravitation, for which you can just derive Kepler's laws. So, and that's a lot simpler still, right? So Newton's laws describe a lot of stuff, including astronomy, but also including what you observe on Earth. And it's kind of extremely compact. So you have the law of gravitation, you have Newton's three laws, and that predicts everything. So the trend here is you try to make a theory that does good at prediction, but that's also simple. And that lets you figure out how to predict the future. And of course, kind of Newton doesn't predict everything. So for some stuff, you need, for example, general relativity, stuff like that. So that kind of comes back to the idea that Occam's razor works really well. So if you are trying to figure out a model of the world, what you want is a model that predicts what you've observed in the past, but also a model that's as simple as possible. How do we bring it back to the context of a neural network? Well, basically, regularization is an implementation of Occam's tracer. So if you do something like clip the weights in the discriminator in a WGAN, what you're saying is, I want the discriminator to be simple. In general, if you do weight decay, what is it saying? It's saying all things being equal, and in fact, even if I'm doing a little bit worse at predicting in a training set, I want the weights to be close to zero. That makes it so that the network is more linear. So in a sense, it's a simpler model of the world because it's approximately linear versus a network with some weights that are extremely large, some weights that are extremely small, which can be kind of extremely wavy, so extremely complicated in the way that the epicycles are complicated. Now, that's probably not the whole of it. I don't think that you can get to Newton's laws with just weight decay, but that is a framework that could potentially work. So back to the octopus. So could the octopus figure out physics? Well, I don't think there is a reason it couldn't if it has enough data. It might be that it kind of reproduces something like the epicycle theory. So kind of the big network is trying to predict what's going to happen. And it's, kind of basically kind of recomputing whatever is the computation be that you do with epicycles. But if it has enough data and if it really tries to make the network, the model, be as simple as possible, it's plausible that it could, of course, after it figures out language and stuff like that, it could start trying to encode something like Newton's laws into the weights, because that's a simple, small network that predicts really well. So would it work? Well, we don't know. It has not been shown to work or anything close to that. So GPT-4 is nowhere near being able to do that. It has been shown to work that you can kind of learn some physics a little bit with in some simple settings, but nothing very general. It's unclear how much data you would need in order to make it work with current architecture. So it might be that with whatever people have now in terms of neural networks, in principle, if you have an infinite amount of data, that would actually work. But in practice, there is not enough data in the world in order to actually make anything like that work. But theoretically, if you have an infinite amount of data and infinite compute, infinite time, I don't see a reason that you would not come up with Newton's laws or, in fact, string theory or anything else.